real pleasure to introduce Lewis Mitchell from Adelaide. He's an applied mathematician, data scientist, data science researcher, specializing in social networks, human interactions, also epidemics and other things. I have been personally wanting to speak with Lewis for a while, and hearing him present a seminar can be a great start. He got his PhD from Sydney a few years back. He's now a senior lecturer in Adelaide and is involved in quite a few projects. You can check out his Twitter handle as well. That's this @Lewis_math. So thank you, Lewis. All yours.
Thanks, Yoni. Yeah, it's great to be here. It's almost like being at home. I guess you made me feel very at home. Please feel free to ask questions in the chat as I go. I've gotten pretty good at throughout the semester at monitoring the Zoom chat and taking questions as I go from that. This talk is a bit different to the sort of talk that I would usually give, in that it's it's quite a bit less complete work than what I would usually talk about. So it's very, very much work in progress. And actually it's sort of a bit of a mishmash of a few different things that I've been working on over the last few months, because, like many other people, COVID-19 has presented a good opportunity to do a bunch of research on using a bunch of different approaches and different data sets for me. And so it also fits broadly under the banner of social media analysis. But it's a variety of different things. So I'm actually not going to give sort of one talk. I'm actually sort of going to give three mini talks, if you like. And it might be two mini talks. We may not get to the third, depending on how long I talk about the first two. We may not get to the third one, and we'll just see how we go. And these are the three talks. So it's sort of like about three different social media data sets. And this has been a really interesting thing about this pandemic, is that tech companies, who are usually notoriously private with the data that they collect on all of us, there's actually been little trickles of data coming from companies like Facebook, who notoriously can never get any data from, and Apple and Google around mobility, and a range of different other tech companies that are actually providing little bits of data for researchers to look at. So I'll talk about a few. So I'll actually start off with a bit of mathematical modeling, so old school traditional mathematical modeling around contact tracing. And then, because it's familiar to me and I like playing with Twitter data, I'll show a couple of the very preliminary results that I've gotten tracking the response to the COVID-safe contact tracing app via Twitter, using sentiment analysis and things like this. And then the most interesting data set I think that we've had access to is this one from Facebook, through their Data for Good program around human mobility. So I'll talk a little bit about that and the work we've been doing, trying to quantify social distancing using some co-location data. And then if we have time, we'll talk about a Reddit data set at the end, an interesting Reddit forum where people report on their experience being confirmed positive with COVID-19. And how we can actually extract something like the arc of patient experience, again using natural language processing, topic modeling, and sentiment analysis to try and automatically extract out what people are, the symptoms that people are having, and the things that they're feeling as they progress through, their coronavirus story. So that's the three topics. So I'll start with contact tracing, and my collaborators with this. There's a really interesting guy called Peter Eckersley, who's a computer scientist by trade, who's worked for as positions with Stanford, and with is a privacy guy now, and works with the Electronic Frontier Foundation. And he's the co-author with James McCaw, star of television and screen and print, some of you may have heard of. He's the co-author of this, it's essentially like a blog post manifesto, website, stopcovid.tech, where they essentially call on tech companies for various things that they could do to try and help during the pandemic. So there's sort of an interesting story as to how the three of us got together. So Peter is a uni friend of James's back from their PhD days some time ago. Peter is Australian, but he lives in the Bay Area in the US now. Got stranded in Australia at the start of the pandemic, at the start of the outbreak. Ended up living at James McCaw's house for a little while, and then through James, I got connected with Peter, and because we were talking about contact tracing and things, we sort of started working together on this modelling project, and then turned into some work around the digital contact tracing and things. Okay, so we had in March when we started working on this, we had a few questions about digital contact tracing that we wanted to try and answer. And the first one, which I think is question 0, which is a non-trivial question for Australia, I think, is, do we even need this? There's been a lot of hype around digital contact tracing and contact tracing apps over the past couple of months, and an exponential explosion in the number of contact tracing protocols and apps and things that are available. But there's a question, I think, at least for us in Australia, is, do we need it at all? And I mean, it's not immediately clear that we do, to be honest, especially as Australia has done so well with other mitigation measures like social distancing, at actually stopping the spread of coronavirus, at least up until now. It's possible that we could get away with just manual contact tracing in Australia, as it's sort of always been done by epidemiologists, particularly when we have high unemployment rates and a workforce that is sort of sitting around looking for work. So in Australia, I think if you wanted to throw money at the problem of contact tracing, you could throw money at human contact tracers and presumably train them up quickly. There's a large workforce there, and we could probably scale that to the extent that we need to. So it's worth mentioning, I think, is that digital contact tracing is not the only solution there. And so if you're going to go down the digital contact tracing route, then there should be a few things that you would want digital contact tracing to do. You want it to provide some benefits over traditional manual contact tracing. So digital contact tracing should be able to do a couple of things. So firstly, it should be faster than manual contact tracing. One of the desirable properties of a contact tracing app is that you find the contact straight away. It takes time, it takes days for a human contact tracer to conduct the contact tracing interview and contact all of the, to phone all of the contacts and identify them, get their details and track them, put them into databases and do all of this record keeping. And that takes a long time. And one of the things that you need to be able to do is you need to identify contacts quicker than they can infect other people, which is something I'll come back to in the model in a sec. So you should want digital contact tracing to be faster than that by being able to identify the contacts straight away. And perhaps more importantly, I mean, digital contact tracing should be able to give you, if it works, something that you could never get from manual contact tracing. And this is the idea of the sort of the so-called friendly stranger, the person that you stand close to in the supermarket line. Woolworths, who you're never going to know what their name is or what their contact details are, but who you might have come into contact with and passed the virus to, or vice versa. So you should be able to find more contacts if digital contact tracing works in the way that we might like it to, than you could do with manual contact tracing. So that was the first question. The other questions that we had in March when we started this were, we very quickly started trying to look at what are the different types of contact tracing protocols, apps that are out there. You would have heard about the Google and Apple API that's been released now for doing contact tracing, and there's some controversy about whether the Australian government should adopt that as opposed to essentially Singapore's protocol. There's also completely decentralized methods coming out of Europe, and a range of different different types of ways of doing digital contact tracing. And so, which one should Australia choose? And then the $64 question for everybody, the major question is, how effective is it likely to be? And then, the big question, if I'm the government, is, what level of adoption, what proportion of the population do we actually need to download this app in order for it to be effective? Indeed, whatever effective means here. So, we sort of wanted to understand eventually, as we're doing this modelling and as the COVID Safe app is coming out, to answer questions like, where does the 40% number come from that the Prime Minister originally put forward as being the number that he wanted the population to, the proportion of the population he wanted to download. So these are the questions that we had. And I go through these because they actually inform some of the decisions that we make in setting up the model. And so here's the model that we wrote down for modelling contact tracing. And in a lot of ways, this is a very simple model. This is a very standard epidemiological model. And in fact, it's not an SEIR model, it's an SEEII model. So I should split the E and the I compartments into two. But otherwise, this is this is the skeleton of the model that is used by James McCaw and Jodie Vernon and team in doing this scenario modelling, which I think you discussed a few weeks ago in this seminar. And this is the guts of it. And so, like them, we have some sort of branching here from the susceptible class. So you can either not get contact traced, and then you progress to the exposed and the infected and recovered classes, or with some probability P, some proportion of susceptibles get funneled into quarantine, and then we don't really care about them anymore in our model because they're not going to infect other people. So there's a lot more complexity than this in the models coming out of the Doherty Institute. But for us, because we're not really overly concerned about people once they're quarantined, we're just going to assume that they're removed from the population. And so this is the model that we write now. So it's actually a simple model, but we do a bunch of sort of complicated things to it. So we bring in some of the complexity around contact tracing by some of the modifications that we make, or the way that we treat some of these parameters. So the first thing that I've got down here, this L1 is a lockdown that we build into this. So, noticing that Australia and other countries were going through this process of locking down in March, April, we build that into the model. So if incidence goes above some threshold, then we basically reduce our effective, essentially reduce the beta parameter here in the model to something that's below 1. And so we get controlling the outbreak through social distancing, through lockdown. That's one of the things that we do. We build in some length of time here. In some versions of the model, we have a maximum capacity for lockdown, and then you just get sick of it. You can't lock down for an entire year, and you open up again and the thing takes off. So these are all parameters that we can play with. I guess, and now the important question here is, while this is super simple, the big question here is, how do you choose this P, right? Like, that's the most important, or perhaps the most important parameter in this entire model for us. And this is where things start to get reasonably complex. So, just broadly, and I'm hiding a lot of the details here, I'll admit, we break this P parameter up into a few different factors, which all get multiplied together. So the first thing is that we're trying to model that you don't have the contact tracing app forever. You launch it at some launch date. So the H here in this is a Heaviside step function. So you get switched on at some rate, and then you can start pouring people into that quarantine class. And you have some adoption rate amongst the population. So some proportion of people, fraction of people installing the app, we build in there. And that's going to be one of the important parameters here. Now, one of the other important quantities that you have here is what I was alluding to before when I was talking about the speed of contact tracing. You have something, we call this, the probability F race, the probability of winning the race to contact trace someone and put them into quarantine before they go on and infect someone else. So basically, we have a distribution of generation times, which we try to look up from the emerging literature as quickly as we can. And then we calculate some probability of the contact tracing tau R being less than the generation time. So with some probability, you contact trace susceptibles faster than they can, faster than the generation time, faster than the time to infect somebody else, and then you move them into quarantine at some rate. And then you have a parameter or a factor here related to testing. And so this is actually probably not so important in Australia, but we wanted to have some generality in the model to be able to model places like the US, which in March, April probably didn't have enough tests to be able to capture everybody. But the idea is here, you can only identify that original contact if you have enough tests, right? So you can only feed people into quarantine if you have enough tests. So that is hiding a bit of complexity here, but that gives you the idea of the model. And essentially, we have now a bunch of parameters on things like these generation times, the time taken to do contact tracing, the time at which the app launches, the adoption rate, all of these different parameters. And essentially what we do is we put distributions on all of those parameters. So I call them prior distributions in inverted commas because we don't actually do any Bayesian inference here. We essentially just take a lot of Monte Carlo simulation. So we sample from a distribution of lots and lots of parameters, and then we were interested in just running the model and seeing what sort of worlds do we get out, and exploring the different types of possibilities that we get for the effectiveness of contact tracing. So you can start exploring some of these parameters. So here I'm looking at the number of the proportion of people who are quarantined via the app, and the colors are showing you just the effect of the launch date. So as you launch the app later and later and later during the outbreak, you quarantine less and less people. That sort of makes sense. And it gets more interesting when you just look at a few samples of these different model runs. So here's a few here. So in the solid lines are worlds where we don't have our contact tracing app. So we have some relatively slow manual contact tracing, but we don't have the additional boost that you get from the contact tracing app. And then you see a bunch of small crosses here, which are the dates at which the app launches. And then we simulate the world in which you have the digital contact tracing going on. And so the y-axis, I'm plotting the exposed proportion, the proportion of people who are exposed, and the same as the number of people who get infected in this model. And so you see that generally the number of people who get who are exposed takes off slower in the worlds with the app than without. We get this interesting sawtooth behavior because of that complicated lockdown idea that I built in. So when incidence goes above some certain threshold, government locks down, R effective drops below 1, and so so things start to wane off again. And then after 30 days, I think it is in this model, in this particular simulation, you get tired of that, you open up again, the thing takes off again, and so you get this sawtooth in a lot of these cases. So this is this hammer and the dance that people were talking about 6 weeks ago, and which has turned out to not be incredibly realistic in Australia, but it's a sort of complex dynamics that you can get out of this pretty simple model, but with some sneaky little tweaks to it. So a few other things. So you can plot the quarantine. So with these same simulations, in each of these cases, I think the number of people quarantined using the app, actually most of them, number of people quarantined during using the app is more than if you didn't have the app, which also makes sense. So that's good. And then the important thing that we can start to plot is the number of days that we spend in lockdown, right? So the cumulative number of days that we spend in this are effective less than one state when we've switched on this lockdown parameter. And the interesting thing here is that you see that in general, you tend to get, with the contact tracing app, some number of reduction in the number of days of quarantine or a number of days of lockdown that you have. And that's the desirable thing. And so that's the thing that we really start to look at. So, another figure that I could plot here would be the reduction in mortality, for all of these different simulations. I won't even show that to you because it turns out that when we try and tune this somewhat for something like Australia, the reduction in mortality for the contact tracing app, sort of regardless of what level of adoption of the app we simulate, turns out to be not very much at all. But there does seem to be some difference in the number of days that you spend in lockdown. And so this is that. So along the x-axis here, in both of these figures, I'm showing the proportion of the population using the app, right? And so these are a bunch of random draws from a uniform distribution over that proportion. And then the y-axis on the left, we've got the number of lockdown days that we have. That we have, in these simulations. And so you can see that as more and more people use the app, as a proportion of the population using the app gets above 80% or so, you see this increasingly steep reduction in the number of days of lockdown that you have. But it's not huge, right? So on the right panel is the one that you really want to focus on here, and that's the difference in number of lockdown days between worlds where we have the app and worlds where we don't have the app. So it's essentially the difference in number of lockdown days between the solid lines and the dashed lines in those figures that I was showing you before. And so this is the key thing, right? Like the key finding that you get is something that you can sort of expect, and something that's consistent with the other modelling that's been coming out in the past few months about contact tracing. You have this sort of quadratic effect. So because in order to do effective contact tracing, both the infected and the infectee need to have your app installed, right? You need to be able to identify both of those. You get this quadratic term where it sort of only goes up steeply once you have a large proportion of the population using your app. So for some points on the curve here, so currently, it's about 25% of the population has downloaded the COVID Safe app, which is pretty high. It's higher than what happened in Singapore. But based on these simulations, which are not entirely realistic, but we've simulated a wide range of possibilities here. That's the important point, I suppose. And we're looking at over a year saving roughly 4 days of lockdown. And there's some variation there. Maybe it's as high as 12, 16 days or something like that. But that's where it sits at the moment. And so you can ask, what about the PM's target? So the original target of 40% of the population downloading the app. Well, that was going to, that's a little bit better, but not much. 40% of the population end up downloading the COVID Safe app, or downloaded it on day one, I suppose, in this model. Then, that would have saved somewhere around 10 days, at 2 weeks worth of lockdown, which doesn't seem like a lot for downloading an app. But then there was some figure that said that for every week of lost productivity, spent in lockdown, it was some tens of billions of dollars to the economy. So I'd be happy to take a 0.0001% commission on that saving for this modelling. If the government liked. Let's see. David has got a good question here. Rather than the unstructured randomness of Monte Carlo choice from the variety of distributions of the parameters, would Latin hypercube sampling of the distributions be worth the effort in giving more accuracy? Very possibly, yes. I mean, what would really be better here would be actually doing some Bayesian inference, which is, a whole other kettle of fish, because then I have to have some observation process and I have to think about the quality of the data. Yes, I mean, Latin hypercube would something that I had thought of at the time as something that we should do, and it just hasn't happened yet. But yeah, that would help us explore these distributions a bit better. Okay, so anyway, so then this came along, in the middle of making these plots, and we were sort of like, where the hell did the 40% come from? And so now we had a bunch of other questions about COVID safe. Firstly, COVID safe uses the same Bluetooth-based approach as the Singapore app. The protocol is called Blue Trace. And so you can ask, is that the best way that we could be doing contact tracing? That's probably not. There's been plenty of debate in the media, if you've been keeping up with it, about the privacy aspects around COVID safe, which I won't go into here, but there probably are better ways to do it. Of course, there always are. Might not be, it's not the worst approach in the world, probably either. But the big question is how many people, and the big question that people were asking us, or asking James, or asking everyone at the time, was how many people need to download it. And that's a bit of a how long is a piece of string question. Like, the first thing to say is that this curve's always going up here, right? Like, there's always some improvement here, and as long as 2 people have downloaded the app, there's some non-zero probability that you'll have some, you'll trace some contact that you wouldn't have caught before. So there's always benefit, but it becomes sort of a different question of how do you define success on this curve. If you make an economic argument about tens of billions of dollars of wasted weeks in lockdown, then 40% is great. And the big question is, will the Australian public trust this app, right? Like, the clear point from all of the modelling, ours and otherwise, is that people need to download these apps. You need to have high adoption rates for them to be really, really effective. And that's where we're starting to think that, well, the first impressions about the app really matter. And so that's where the social media comes in here. So being very excited about this, I from a few hours before the app launched, so that's actually the first dashed line on the second figure here, I started collecting tweets about COVID safe. Just any tweet that contained that phrase COVID safe, a very nice Twitter collection to do. The figure on the left shows you, and this is a couple of days worth of tweets after the app launched. I'm still collecting, so we have a lot more now. I just haven't analysed them yet. But for Australian tweets, 14,000 tweets in a couple of days is quite a lot. So there's quite a lot of discussion about it. And the thing that you noticed is that in the very early stages, the people who were talking about the app happen to be social media influencers, whether you like that term or not, in very heavy inverted commas. But it was people with a large number of followers who were tweeting about the app early on. And that's interesting. So then you want to look at what were those people saying about the app? What was their attitude towards the app? And it turns out that it was pretty negative. So I went back to a sentiment analysis algorithm that I've known and loved for many years called the Hedonimeter. I don't need to talk about it now. It's basically a dictionary of happiness of words. You have scores assigned to different words. You calculate the sentiment of a bag of words, so all the tweets within an hour or something, by calculating an average score, essentially. And so this is about baseline for most tweets, or 6 or so in normal times. And you see, this is actually a decent dip here very early on. So people with a high social media reach tweeting negative stuff about the app early on, which is something that I would want to know if I was the government. This spike over on the right here is in the middle of the night. It's about 4 a.m. Or something. There's a small number of accounts tweeting very, very negative stuff about the app. So that feels a little bit bot-like to me. And that's something that will explore. So some sort of hashtag hijacking going on here, and something that we want to explore. So fortunately, we've got some funding from the Cybersecurity CRC to do this. Yoni, yeah.
Could that have been the night where they released the open source? So about 2 weeks
No,
after.
well before that. So this was only this is only a couple of days later, actually. Here. So yeah, I mean, this is really this is a huge dip. So I really need to go in and look at exactly what these tweets are here. But yeah, it's likely some sort of hijacking of this hashtag, possibly a bot or something, just collecting up any hashtag that's trending at the time and spamming something out on it. I'm going to read Michael's question here. I guess my take would be that there's something better in terms of who downloads it. Matters more. I've downloaded it, but I've got no friends. Yes, you do, Michael. I'm your friend. Would the impact of Barnaby downloading it be greater or more controllable? Would be optimal not to download, but to get a friend to do so. You're getting toward at the end there. You're getting towards another question that I love, which is the friendship paradox. Which, yeah, I mean, it's always better to get somebody else to download the app, because then you're more likely to hit the hubs. Yeah, I mean, this is more about just the public response, public sentiment around the thing. I think part of the explanation for this is that you had sort of people who were very interested in privacy concerns complaining about it, and the thing wasn't working very early on as well. And so that's what the chatter is about. One more figure on the sentiment stuff. So it seemed like the sentiment sort of leveled off for a time, but looking further, so here's now a couple of weeks, a week or so into the future, you see the sentiment start to dip off. This is possibly around about when they release the source code, but I need to go and look at it further. So yeah, I mean, there's interesting more work to be done here at tracking this sentiment and looking in more depth at what people are talking about later in time. Now that semester's over, maybe I'll actually get to do that. That's the in progress part of this talk. So a couple of thoughts to sum this bit up. So we're yet to see the potential benefits of digital contact tracing, right? In Australia, we don't have many contacts to trace. So I think the jury is still out on whether COVID safe is good or bad at the moment. The thing that our modelling and any modelling that you're going to do on contact tracing, I think, will show is that there is also always some benefit to installing the app. And in terms of, if you think in terms of the economy, days of lockdown saved is actually an important thing. But this quadratic effect where you see this takeoff only for very high adoption rates, 80% or so, sort of a killer. And we're never going to see 80%, I don't think, in Australia unless something very unusual happens. Yeah, and what's been interesting for me as well is that there are almost certainly better decentralized, more privacy preserving protocols out there for contact tracing, for digital contact tracing, and COVID safe's probably not the best thing that we could do. In a lot of ways, it's not the worst that we could do either. It's been interesting to see how it's become sort of totemic for Rorschach test for how much people trust their government, and so you're seeing that in some of the chatter around the app as well. And so the Twitter and the social media analysis will delve into some more of those issues. So that's the contact tracing bit. So ask questions in the chat, and we'll come back to if you have them. But otherwise, I'll go on to the next thing that I want to talk about, which is Facebook data. So the white whale for people who study social media and online social networks like I do is to get some data, any data, out of Facebook. And famously, because you are the product in Facebook. There's no incentive for them to give up any data usually, and so they don't. So it's been exciting that there's been a little bit of data available from Facebook because of the pandemic. So, yeah, my collaborators on this. So Cameron Zackerson is a very clever postdoc who has been at the University of Sydney, now is at the University of Melbourne. Has been supervised by Nick Keard, and also Joshua Ross from Adelaide Uni has helped with some of the interpretation of some of these probabilities and things that I'll talk about in a sec. So, okay, so Facebook's released some data, we've done some things with it. So here's a picture that is my estimate, my best go at quantifying contact tracing. So, sorry, at quantifying social distancing in Australia. So the three red lines are when the Prime Minister made various announcements, locking down to various degrees. So this is something like, the first red line is the 500-person announcement, and the 100-person, and then the essentially 10 people in a house. So various stages over that crazy couple of weeks where we locked down. And what I'm plotting on the y-axis here is a measure of the average number of contacts by a person in each of these different states. So in the Northern Territory and in Tasmania, people have a relatively low number of contacts, much higher in Victoria and New South Wales, but everywhere you see that those social distancing measures worked. People stopped coming into contact with each other. And it's been waning very slowly since about Easter. Surprisingly to me, not as much in recent weeks. I guess this only goes up to a week or so ago. But it has not been waning as much as I would have expected. So the question here is, what do I mean by a contact, and how did we come up with this? How do I come up with this beautiful, well, terribly beautiful, interesting figure? So the answer is Facebook released some data through their Data for Good program. So there is a few different data sets. So essentially these data sets are all from aggregated data on users of the Facebook app who have location services turned on their phone, and they keep it turned on their phone. Now that's a small number of users. Facebook is a bit cagey. They won't give out demographics on these users for obvious reasons. But they say that it's of the order of a few percent of their user base. So it's not huge, but it's sort of a unique data set. So there's four major different data sets. So one's on user movement. So they have the number of people who move between pairs of small tiles. So they grid the world up into these small tiles. And they also aggregate this data up onto local government area resolution. And they give you the number of people who move between regions in an 8-hour peak period. So essentially traffic matrices. Another one is the proportion of users who stay put. So if you're in the same 600-metre square tile for 3 different hours over the course of a day, percentage change in movement range, so the number of different tiles in which you were present in compared with some baseline. And then the most important one for me, the one that I've been using in that figure, is there's something called a co-location probability. And so they define that as the probability that users from 2 different regions, so 2 different local government areas, were in the same 600-metre square tile during the same 5-minute interval in the past week. So that's a bit of a mouthful, and I had to sort of sit down and do some basic probability and figure out what this means. So let me, most of the game here was convincing myself that, and getting Facebook to confirm for me what this co-location probability is, and it's this. So let's say you have 2 regions, region I and region J, and there's 4 people in region I and 5 people in region J. And then the world here will be broken up into 3, you'll consider 3 of these little 600-metre square tiles that exist just somewhere on planet Earth. So it's not tied to these 2 regions, it's just you grid up the entire world and you look at the number of people who pass through these tiles. Okay, so in one 5-minute period, so in the first 5-minute period in the week, you have a person from region I and a person from region J. They go to this 600 metre square tile and they pass through it in the same 5-minute window. So you get one contact there. So Facebook defines a contact as being passing through that same tile. So it's a pretty coarse definition of a contact, and you could have passed through this quite fleetingly, but that's what it is. And so 2 other users pass through a different tile. So this is a tile in Brisbane, this is a tile in Adelaide, and then there's a tile in Wollongong here, which nobody passed through because nobody goes to Wollongong. 5 minutes later, somebody else passed through the tile in Adelaide. I think I said that middle one was. So the 2 users, maybe they stayed there for the next 5-minute period, maybe they went away and come back again, or they came into contact again. And then in the third 5-minute period, 2 people went through the tile that's in Wollongong. Good for Wollongong. And then, the rest of the week happened, in this process. This process continues. So what the co-location probability is then, it's the number of those, the total number of those contacts that happened, right? So these people were jiggling about, moving around to other places throughout the week. But the thing that we count are the number of passages through those tiles, divide by the population of both regions, and then dividing by 2016 is the number of 5-minute intervals in 1 week. So this is a weekly number. Put those things all together, and you get a probability that's a small number. Facebook basically reports us. They report us the Facebook populations in each region, in each local government area per week, and they report these numbers. So these co-location probabilities between different regions, sorry. And in general, you can write that down, the co-location probability. So long as I and J are different here, they have a slightly different formula if they're the same. But it's these sum over all tiles, sum over I, sum over J of these number of 5-minute intervals, in which you have these co-locations. Okay, so once I've got that, once I know what that is, well, now I can reverse engineer that using basic math that I learnt in my applied probability course, my probability and statistics course, to actually calculate a measure of the average number of contacts per person. So that would just be summing over all of the regions J, and you get the average number of contacts per person in region I. And you can also map that up to the state level. So if I think about all the regions I in the state, then if you sum up this quantity overall I and overall J in the state, and you can get the average number of contacts. And so from that, you can start to get some nice maps. So here's where I'm going to jump back to here, and then I'm going to share a different screen, which will be Safari, and hopefully you can see this. So now I can start to make some nice maps. So on this website, I've put a bunch of different types of maps. Essentially, I can consider contacts that are made between with a region and everywhere outside of that region. Look at also incorporate contacts that are made within regions, and then look at I can calculate some measure of mixing, so the ratio of contacts that take place externally compared to all contacts. So the fraction of contacts that take place outside of your region relative to all contacts that you make. And so you can make these beautiful maps. And the thing that you notice is that, let's zoom in on Brisbane, I guess. I don't know much about the geography of Brisbane, but let's do it anyway. So this is a percentage, measuring a percentage change from some baseline. So the first 3 weeks, there's no change by the way I've defined it. And then you see that red means more people are staying home. And so you see around Easter, it's maximal staying home. and then it's been waning ever so slightly since then. And the interesting thing that you can maybe pick up even from this is that there's some suggestion, to me at least, that the outer suburbs, places which are a bit out of central Brisbane, seem to be staying home a bit less than maybe people in the centre of the city are. So if I completely randomly choose that there, it shows it quite well. And that seems to be a common feature here. I'm not sure why. I'm going to go back to wherever I put. My goodness, where is it? Where have you gone? Sorry, I've lost my actual talk now. Oh, I know why that is. Sorry, very unprofessional. Give me a minute.
It's okay. His keynote disappeared.
Yeah, keynote's disappeared. It's back now. There it is. Is that better? Do you see this? Keynote back?
Yeah, thanks.
Cool. All right, so yeah, that feature of it seems like the outer suburbs are waning a bit more quickly in social distancing than the inner suburbs seems to be maybe something that you see in other places around the country as well. Now, there's a lot of potential. I'm treating this with a lot of caution because there's a lot of reasons that might be, including just statistical regions. We haven't really controlled for the relative size of each of these local government areas, and they can vary quite a lot. But it's possible that the outer suburbs might be waning in social distancing quicker than the inner city is, which would be an interesting find. The other thing that we can do with this is we can start to think about doing some risk mapping, right? So if I have these traffic matrices, so count the number of people who are moving between regions and have these co-location probabilities, then you can start to think about, well, what if I see an outbreak in some region? So the Cedar meatpacking family is in this red LGA here, that's Brimbank. And we can start to think, what areas around there might be at higher risk due to people moving around. So, so Cameron Zackerson's been leading this, but yeah, we've had some ideas of ways that you could come up with some risk maps there. So, so in some sense, this plot's not totally surprising, right? The suburbs, the LGAs that are immediately around the meatpacking plant are most at risk, have the highest probability of transmission. But you see some, there's, it's not completely just concentrically radiating outwards. There is some non-trivial structure here. I think it's probably not surprising that central Melbourne there is at higher risk because it's got a higher population there. But that's the sort of thing that we're thinking of doing. Now, Yoni, how long have I got?
Yeah, I mean, this taken a few minutes more if you need.
So I think I reckon I'll stop there so that you can ask questions. I won't do the Reddit Reddit example, except for very briefly. Yeah, maybe I'll just say that, yeah, the co-location data is interesting, I think. So it's really a criticism that you could level at it is that it's incredibly coarse. All you need, it's not measuring real contacts like we're thinking about them with contact tracing. It's measuring the probability of passing through a 600 meter by 600 meter square. That's pretty big, right? And just being present in the same, in that same region is not, you could be driving on the freeway, and totally miss people. So this is certainly overestimating the number of contacts grossly. But it's unique. There's not too many data sets. If you look at the data sets that Apple and Google are providing, they're giving you numbers of people moving between different regions. It's nothing that pertains to be about contacts. COVID Safe is we're not going to get any data as researchers out of COVID Safe, and rightly so. So, this is, to me, the closest that I can think of that might give something that's related to actual contacts between people. So yeah, I mean, it all shows that social distancing is waning, but slowly, you know, much slower than I would have expected, or that seems like is happening. You know, walking around the city myself, anecdotally. Yeah, the interesting thing here would be if there's some variation, true variation between urban and peri-urban or regional areas. Yeah, and I think the really useful thing that we can do is this application to mapping risk, and you know, the reminder there that transmission's a network phenomenon. So I'll stop there. So I won't do the last example, except to say that there are some beautiful pictures associated with this final example, and you can look at them at this on this preprint that's on the archive that you see up in the top right there. So yeah, I'll stop there. I'm happy to chat and take questions. We have them. Thanks.
All right, thanks a lot, Lewis. We typically do a real clap, a real human clap. So 3, 2, 1. Thank you.
That's nice. That's charming. I really like that.
A lot of exciting stuff. I'm sure there are questions, so shoot away, everybody. Oh, Michael, go ahead.
So, hi, Lewis.
Michael.
Apologies, I've been kind of flitting in and out of your earlier talks. I might have missed something, but I've been asked by people in WA to try to evaluate the risk associated with remote Indigenous communities. And my question is really around data. Do you see any data out there that, my problem is that we have no way of quantifying people moving between remote Indigenous communities and more centralized locations. You mentioned the data you have is a fairly coarse grid. Is this the best we can do?
Well, it's the best I can do for the moment. That's for sure. So interestingly, with these Facebook mobility networks, you don't get nothing in remote regions. In fact, you saw a large number of at first you saw a large number of people going to a region in South Australia that was very remote, which was possibly a mining. You saw some people with a Facebook app going to various mining locations. I think you're probably not going to see anything in remote Indigenous communities, although social media penetration is not zero. Indigenous communities, so possibly.
I apologize if I missed this, but have you got data from Google at all?
I mean, we have data from Google, and you have data from Google, and yeah, that data is publicly available. Pretty sure it lists only a bunch of capital cities. So Adelaide is there, but that's going to be it for us in South Australia. So yeah, remote communities are difficult. I know that this the Doherty Institute group, so the Jodie McVernon, James McGaw group, are definitely looking at that. But yeah, I think it's my impression. I think it's largely modelling based. Data's going to be difficult to come by.
Okay, thanks.
Oh, sorry, I was muted. Are there more questions? So, Lewis, I'm very excited about those graphs. I have 2 questions. So, and Twitter was also excited. I mean, I saw that there was a lot of traction there. I guess this graph is already useful, those plots that you've showed, just to see if when restrictions are lifted or reinstated, to immediately see if there's a change or not. And I guess, can you do this almost in real time, or is there a delay of a few days?
So there is a delay of a few days. So with this co-location data, and I was attracted to this because it allowed me to actually calculate something calculate a number rather than a percentage change that was sort of meaningful, or interpretable, I guess. So there's a delay of a couple of days, and it's all averaged over a week anyway. So you get the data averaged over the previous week, a few days after the end of that week. So it's not, it's not as real time as some people might like there. Some of these other data sets are much more frequent. So let's say the movement data comes out, roughly every 8 hours. So the number of people who are moving between different locations comes out much more regularly. So if you wanted to do something real time, closer to real time, that would probably be the data set to use, I think. A thing that sort of worries me about all of this is it's we're getting this all at the goodwill of Facebook. I could cut off at any time, I suppose, or whatever the back end of their Geo Insights platform breaks down. So it's all a bit tenuous, but I think it's useful to use.
Gotcha. So I had a second question about you're finding that there's more co-location movement in rural areas. Could that be an artifact of the fact that when you look at rural areas, there are only 2 or 3 access roads?
Yeah.
So people need to pass through that same block, whereas movement within an urban area does not happen.
Yes, it absolutely could be that. And it could be just that you have to move about more. In rural areas are also sparsely populated areas, so to get to anywhere, to do anything, you have to move a larger distance, so it could be related to that. So we need to control for a bunch of things, including population density, I suppose you're right about a number of access roads. There's nothing stopping 2 cars that's moving past each other on the highway, on the freeway, being classed as contacts here. So some measure of that might be useful to look at as well. So there's a lot of validation that needs to be done, and this is all reasonably preliminary at this stage, but it's still interesting and surprising to me that even in this coarse measure, this waning seems to be slower than what I would have expected.
Right. Oh, interesting. Thanks. Are there more questions? Thoughts? They sometimes pop after a second or two.
You're welcome, Cecilia. Thanks for coming along.
Okay, so I'll send a link to the YouTube video, and also so there's an archive paper about the third topic, Reddit, we'll have to invite you again, maybe even not virtually at some point.
Yeah, that would be great. Please don't hesitate to contact me if you've got any questions. Yes, and I would love to. As soon as we can travel again, it would be lovely to come and visit, and likewise.
Okay. Yeah. Thanks again. Let's thank Lewis again. We can do again the 3, 2, 1. Good night, everybody. Thank you.
Good evening.
Bye-bye.
Thanks, Lewis.
Thank you.
Thank you.
Thanks, Lewis. Have a good night.
You too.